So good afternoon, everyone. Welcome to the second lecture of the mini-school on mapping the initial condition of the universe and exploring the cosmic microwave background. And my apologies if we started 1 minute late, but there was a tiny little Zoom hiccup. Yeah, but anyway, we are all here, and we're all looking forward to listen to the second lecture by Martin Bucher. I introduced Martin last week, so I don't have to reintroduce him. The only thing that changed in his distinguished CV is that this week he's in Durban. So you are attending now a mini school where the speaker is physically in South Africa for a change, yeah? And hopefully this is a good sign, which means that there is some hope that normal times are coming back. Yeah. So Martin, sorry, people are not here to listen to me; they're here to listen to you. You already started sharing your slides, so if you would like to start your presentation, you're most and welcome.
Okay, yes, I'm in Durban, and I'm at the house of a veterinarian with 3 cats. So people shouldn't be surprised if a cat joins the, the discussion. So this is the second of 4 lectures, and we spoke bit about Big Bang cosmology and general relativity and all of that. But today we're going to cover more the theory of the microwave background and how it's imprinted. And I will show a few slides with observations because it sort of doesn't make sense not to illustrate some of the points with some observations, but I won't go into observations in any detail until the next lecture, where I will talk a bit more about statistics, how one makes measurements, and the current state of the data. So this is theory, and then the last lecture is going to be a bit the future. What are some of the things that are still waiting to be done, other than, you know, narrowing error bars with things that have already been measured. Okay. Let's see, I will, where we left off was discussing inflation and how it worked, that we did. I'm going to just repeat a few slides from the previous lecture in order to put you in the right mindset. So this is the slide where we looked at the horizon problem. So delta X here is, you know, how far can light or a signal that doesn't go faster than the speed of light travel from the Big Bang to the present time. And we saw that if this integral converges, then you have this so-called horizon problem. And if it diverges, that is, diverges in the past, then any 2 past events can be connected by a common event. And we looked at this sort of conformal diagram. So conformal means you sort of shrink by a constant factor, and light goes by 45 degrees. And we saw that there was a problem that you see we're here and you see the microwave background temperature, and there's no way a signal could have come from some past event. So why is the temperature here within 1 part in 100,000th of the temperature in the opposite side of the sky? So that is one of the things that inflationary cosmology seeks to explain. And the way inflation works is, so this looks like potential that is m squared phi squared over 2. It wouldn't really have to be that. And if we didn't have an expanding universe, then it would be sort of like a simple harmonic oscillator for all the different modes. And we're in particular interested in the, zero momentum mode. And, that would sort of average out to a massive particle. So if you had sort of an axion field, that's sort of what happens. So if you studied field theory, this would all be, very familiar, but if not, this sort of looks like from your beginning classical mechanics course that you have a harmonic oscillator with some potential, but then there's also a friction term, except that the friction comes from the expansion of the universe. And you sort of put in the numbers, and you find that when the displacement is of order the Planck energy, then this term is very important. And otherwise, just what you've learned is correct. You can ignore this first derivative term. And what we want to do to solve this problem is we want to have the expansion of the universe speed up less quickly as you go back in time, and then we can make this integral diverge. So we look at sort of the extreme. Well, let's throw this second derivative term out, and you just have this sort of friction term. So this would be like in classical mechanics, an overdamped oscillator. And it turns out that kinetic energy contributes negligibly to the stress energy. And so you basically have the pressure tuned so that if you expand, the density doesn't go down. So you have a constant expansion rate. So this is exponential or quasi-exponential expansion. So we say quasi-exponential because there is some rolling down, and you want inflation to end. You want to create entropy in ordinary particles. And basically, this field sloshes back and forth. It's coupled to other fields, and it creates particles and the ordinary matter radiation equation of state. And it's just a way of changing what happens at the very beginning. So we can do this integral, and I mean that time goes to minus infinity, but the question is whether this integral diverges, and it does. So that is a good thing. And this was proposed in the early 1980s, and there were also some papers in the late 70s. It's very hard to assign the credit, but Alan Guth was a person who explained how this was a good thing, and this would solve the paradoxes that Robert Dickey and probably others pointed out earlier. Another thing that people were very worried about was magnetic monopoles. So this was a time when the Standard Model was extremely successful. And so there's SU2 cross U1, and let's include QCD in the Standard Model. And if you put that in a larger group, then like SU5, then you get these magnetic monopoles, and they would be the dominant form of matter in the universe. And people like Guts, they had a higher opinion rating than today, where people are not as convinced, and that was historically one of the motivations of inflation among particle theorists. The other thing to think about here is that as a classical theory, this fails, because when the universe expands exponentially, and I'm not going to, these lectures are informal, so I'm not going to work all of this out. You can find it in papers and books, but you will find that this quasi-exponential expansion, it just stretches and stretches and stretches, and what you have is stretched vacuum. And it's very smooth, but it almost works too well without quantum fluctuations, because you would create a universe that has no irregularities, and we know the universe today is irregular. So you want to have some irregularities, if you would like to have a pattern that is matches the observations that you see today. So quantum mechanics saves the theory. And let's see, I'm rearranging my window so I can trying to get this bar out of the way. So here in red, you have a potential, and then this black curve is supposed to represent the ground state wave function. And for those of you who haven't studied quantum field theory, I mean, this diagram is like from introductory quantum mechanics for a simple harmonic oscillator. But the field theory, when you don't have nonlinearity, can be decomposed into an infinite number of harmonic oscillators. And the Fourier modes have this wave number dependent. So each of them is independent and each has a wave function like this. And if you have just a finite energy, then the very ultraviolet modes have to be in the ground state. And then when you stretch and you stretch and you stretch, well, you see those that are in the ground state. And that sort of gives you a unique preferred vacuum. So you get a prediction for the initial conditions, which is quite unique in physics, because most physics doesn't tell you what the initial conditions are. It just tells you how things evolve forward in time. Let's see. Oh, okay. The next thing we're going to talk about is what does the spectrum of perturbations look like? And before I talk about that, I sort of want to explain to you, I mean, we use how quantum fluctuations could possibly have anything to do with the large scale structure of the universe, because we usually think of quantum fluctuations as something that is relevant for small things, for atoms, for short distances. If we would just take a scalar field and look at the two-point correlation function in the space, it's not expanding just on dimensional grounds, you know that it's going to fall off. It must scale as energy squared, so it's 1/r squared. So you would think, well, if I take this really tiny measurement on small scales, then I would have a big fluctuation, but not on the size of the universe. So that argument is more or less right. But in inflation, the universe has a very rapid expansion rate that doesn't change for a long time during inflation. So you get these scales that so-called leave the horizon, and that means that the friction term becomes relevant and sort of freezes in their amplitude. So at one time, all of these fluctuations had an amplitude of 1/, this expansion rate during inflation. So it was short distance and all at the more or less the same short distance. And that gives you this, wait, don't know why my arrow keys aren't, let's see. Okay, now they work. Okay, so this is there should be an equal sign here. You get, this is a definition of the power spectrum. So these are 3 vectors. And if you want there to be no scale, then you want this integral to be logarithmically divergent. So that means that if I sort of take a snapshot of the scalar field and I put it in a photocopier and have something at twice the resolution, it looks exactly the same, and that can be repeated and repeated. all of these derivations can be done a lot more carefully, but I'm sort of giving you the intuition behind what's going on. So you get this logarithmic divergence. So should we be worried about the logarithmic divergence? Well, if you think about it carefully, you're sort of looking at distance differences in the potential. So the low k part, well, that's because there is no average. And if you take a larger and larger volume, then the average keeps on jumping around. But that's nothing really blowing up. And then on smaller scales, there are other things that cut off the divergence. So this is that you should get an approximately scale invariant spectrum of density fluctuations. This is one of the predictions of inflation. So this was discovered by, well, the history is a little complicated, but there was this conference in England with, it was actually near Oxford, financed by the Newfield Foundation. So it was called the Newfield Workshop, and Alan Guth, Stephen Hawking, Andre Linde, Paul Steinhardt, Jim Bardeen, and I've probably forgotten a few people, Starobinsky. They were out there and they were comparing their calculations, and eventually there were sort of, I think about 5 papers that came out of that where they calculated in different ways what was the prediction. So there's a lot of sort of serious general relativity gauge fixing. I'm just giving you a hand-waving explanation of why the final result makes sense. Okay. Well, I was going to talk about observations next time, but I'll just put in this rather old slide to show you what's how to plot the observations. So you see these multiple moments, and they're multiplied by L plus 1. And that is the equivalent of scale invariant spectrum in 2 dimensions. It would be L squared rather than L to the minus 3. So you sort of get the number, the square of the temperature per logarithmic interval. And so scale invariant would be just a horizontal line, but you see these oscillations. And these oscillations are exactly that the baryons and the photons are sort of springy, and they all start with a certain phase. So they're sort of let go as the expansion of the universe slows down, and that friction term becomes less, and these modes begin to oscillate. And you see these oscillations, and you also see that the oscillations are damped. And you see here, and the data is a lot better, but there's sort of this rough agreement. So the thing that you should understand is that this is power per logarithmic interval. These are micro Kelvin squared. Sometimes people we'll take the square root, and there are different ideas how to plot this. But this plot highlights deviations from scale and variance. So this is sort of intuitively how you should understand these CMB plots. And we'll talk more about this in the next lecture with the observations. Okay, let's talk a little more about making predictions. So I think this slide is the sort of pie chart, where is the mass density or energy density in the stress energy tensor, how does it break down? So one can make alternative models that have different exotic components, but this is for the so-called concordance model, where you just include the components that you're sort of forced to have. So atoms here is baryonic matter, and that's just 4% of the critical density. So the critical density is that if we have a spatially flat universe, then there's this h squared is equal to 8 pi g over 3 rho. And then you can measure the rho crit, and you can measure the different components as fractions of the critical density. So we have 4% atoms, which is sort of stars, baryons, but baryons include leptons. Then you have the stark matter, which doesn't interact, and then there's the stark energy, which is like a cosmological constant. Okay, I'm going to skip this. Well, let's talk a little about the universe being transparent and opaque. So we'll talk about the Saha equation and how to do some calculations. But basically, when the universe expands at a certain point, the temperature goes down, and to the extent necessary, so you get almost all atomic hydrogen and helium and whatever. And the microwave background photons are long wavelength, so they hardly scatter. I mean, there would be Rayleigh scattering, but that's sort of more sunlight, not microwave. So they come to us almost without free scattering, whereas when the universe is ionized, they just have this random walk, and it's sort of like this fog if you're looking back at time. So we just see this, the sort of edge of the fog, and that's the microwave background. And we could correct this picture, but we can't really see back to inflation. We just see at time before that. What are the initial conditions described by some power spectrum and almost scale invariant equation of state? So that's sort of what is going on. Here I put in a slide with sort of different expansion history, but I won't go through this in any detail. So how do you do some calculations? Well, in this business, there, if you want to compare with observations, then you have to make predictions to the percent level or a bit better, you know, in order to test models. So you need to make your theoretical predictions to match the quality of the observations, and also the fact that you only see one sky. But rather than describe codes and lots of effects, it's good to have a sort of oversimplified treatment where you sort of figure out what's going on, and you know, it'll be right 10%, 30%, but it also lets you, gives you an idea, well, if you change such and such, how would that change the observation? So here we look at how to calculate the ionization fraction, or the fraction of the electrons that are unbound. So you have a process where you can have, let's just take hydrogen, a proton and an electron that are dissociated, or they can be bound in the form of atomic hydrogen. And there's sort of two factors. There's the exponential Boltzmann factor, and there's also an entropy factor. So if you just looked at this factor, you would think, well, at 13 point, when the temperature is 13.4 electron volts, you know, you get half half atomic hydrogen and half ionized. But since there are so many more photons than baryons, entropy really lowers that factor. So it's around 3,000. And here we have, this is redshift, and then this is the ionization fraction. And this is a logarithmic scale. So this sort of tail of electrons that couldn't find partners, or protons that couldn't find their partners, is really small and negligible. Here the assumption is that everything is in thermal equilibrium, and that is not completely true. So you need to do these sort of rate equation codes, and it's a bit of a mess. So that's to get things at the percent level. There are lots of things like this. Okay, so this is a summary. I'm not going to go over this. I think you know it, that you have this, you know, very nearly perfect black body, and it has this temperature that's been measured. The universe is about 13 billion years old today, but this sort of edge of the fog is, I mean, it's not very well defined. So, but the center of the fog is about 380,000 since where the Big Bang would be if you didn't have inflation. And the other number to remember is that these perturbations start out at about 1 part in 10 to the 5. Okay, we talked about this. Let me show you another plot, and this is to put the sort of CMB in perspective. So why are microwaves so important? And this touches on a sort of general theme in astronomy, that when you look at different wavelengths, you see different things. So here we have, about the millimeter, centimeter scale, but it looks like a Boltzmann distribution. And if you look very carefully, that's exactly what it is. Then here's the cosmic infrared background. And by background, what is meant is things that aren't resolved as point sources. So this is a little subjective, but this is dust. So the dust in the interstellar medium of galaxies has a temperature of about 20 Kelvin. So you see a peak, but this is not so close to black body. Here you see this is UV optical background. So these are the stars, unresolved starlight, X-rays from quasars, and then gamma rays from all sorts of weird events. And then you get synchrotron radiation. So the microwave band is here. So if you want to see the Big Bang, you have to choose these low frequencies. And there's not so much energy in here, but almost all the entropy in the universe resides in the microwave background. There's no reason why it has to be that way, but stars, the starlight and the microwave background have sort of comparable energy, but the starlight, of course, is entropy generation, but not really that much. Okay, I think we looked at this slide last time, and you see the monopole, you subtract it off, you get the dipole, and this is from Kobe, and you see the galaxy. And then the fact that these features, you see them in different frequencies by a factor of 3. I mean, there's more analysis indicates that these are fluctuations of the black body temperature and not just something else. So how do we analyze such maps after we get rid of the galaxy? So this goes back into theory. And if you have a statistical process that is isotropic, so there's no preferred direction in the sky, that with respect to the generating the perturbations, each map will have its peculiarities, but you're interested in the underlying process, then expanding in spherical harmonics makes a lot of sense. So we have these ALM coefficients, and they're related, their correlation function is because of the isotropy, can only depend on L, and there's no sort of off-diagonal coupling. So you can, this is just, so these triangular brackets mean it's sort of an ensemble average, and our sky is just one element of the ensemble. So if you believe the isotropic hypothesis, which you can test, you can see if the anisotropies in the northern hemisphere are greater than in the southern hemisphere, and there will be some fluctuations. I mean, it's not going to be exactly the same, but are they statistically significant? So there's been a lot of work done on that, and well, maybe we'll talk next time. I bet there's some evidence for anisotropy in the process, but if there isn't, then you just reduce to these a power spectrum that just depends on L, or equivalently the angle between the, a pair of points. And let me at this point explain cosmic variance. So basically, for each L, somebody has this random number generator, and it gives you realizations of a Gaussian, but you only get 2L+1 of these. So you can take the average power, but it's going to fluctuate. And so you'll never know the real, theoretical variance of the process. So this is called cosmic variance, and it's quite different from other things in experimental physics, because usually you think, well, I have a statistical error in an experiment, that I can run my experiment longer, and then the error will diminish as 1/√² of time. But here the experiment has already been done at the Big Bang, and unless you wait another 10 billion years, you're not going to see more of the universe. So this is one of the limitations, and you don't want to, you want your experiments to approach or exceed slightly the cosmic variance limit, but beyond that, you're just sort of stuck. You just get to see one universe. So this is something unique about cosmology. Well, here we are a little more formal about this, and each of these elements of the power spectrum obeys a chi-squared distribution with 2L+1 degrees of freedom. And here, under the assumption of Gaussianity, we can write down the likelihood. And so you do all the algebra. This is how you can accurately, you can measure a single moment of the sky power spectrum. Okay. Well, there's one assumption that I've sort of swept under the rug, and I've assumed that there's Gaussianity. And in inflationary theory, there's very nearly perfect Gaussianity. There are predictions for non-Gaussianity, and people have been searching for it. But this is sort of one of the surprises. So if you look at older books like the book, what is it, Large Scale Structure of the Universe by Jim Peebles, which is pre-inflation, they, he explains how to analyze the data with a Gaussian distribution. Why? Well, probably just lack of anything else. That's what people do. But with inflation, there was sort of a rationale to believe that that would be a very good approximation. And if we have some time, we can talk about bispectral non-Gaussianity and searches on non-Gaussianity. So that's sort of one of the important observational results that would rule out broad classes of theoretical models. Okay, this is the Lowell Spectrum, is seen by Kobe, and you can see that there are these huge error bars and things fall apart. So this was a very exciting time. This is when I entered the field, and everyone was trying to guess, well, what is the continuation to L of a few hundred and a few thousand? Let's talk about the Sachs-Wolf formula. So this is a very nice formula that you can write down that gives you a lot of intuition about what you're looking at. So this is the fractional change in temperature looking at a direction, which I write as a unit vector. And you have a number of contributions. So if the baryon photon plasma, or the density is higher, then you get a higher temperature. Then you have a Doppler contribution, and then you have a gravitational redshift. So in an appropriate gauge, this can be thought of as your sort of traditional, Newtonian potential Gm over R, although it doesn't really necessarily have a source in the same way. And here you have a so-called integrated Sachs-Wolf term, and that this is conformal time. So the time coordinate where photons travel at 45 degrees. And you sort of see that this term doesn't arise unless the potential is changing. And what happens if the potential is the same, you go, you the photon, you fall into a gravitational well, it gets blue shifted, but then when it comes out, there's a redshift that corrects for that. But if the depth of the well is changing, then you get such a contribution. I won't talk about gauge and all of that, but you can sort of, by using different coordinates, you can make this term go away, but then you'll get other terms that make up for it. If your coordinate system moves with baryon photon plasma, then you wouldn't get any Doppler term. But when you take all of this together, the other approximation is, well, so here we have a sort of diagram of what you're seeing. So you have this sort of light cone, and then this is constant time, cosmic time increases in the upward direction. And you're sort of seeing the conditions here. But this assumes that the universe becomes transparent instantly, and that it was completely opaque, and the truth is more complicated. So in the early 90s, we wrote codes that's not a lot of work, where you can compute the temperature fluctuations using this formula, but you need to take into account that this is a fuzzy surface if you want to do things at the percent level. And this is where the formulas don't become very enlightening. So this is the linearized Boltzmann equations, and you have at each point there the angular correlations of the the angular moments of the photon velocity function. So we fix a sort of plane wave dependence, and you get an infinite number of equations, and then it has to be truncated. And that's what these codes, Camber, class do. And they've all been very cleverly written to run in a reasonable amount of time. Let's see. Okay, let's see, how are we? Well, we have about 6 minutes left. And I want to leave some time for questions. So I will sort of end with this slide and the next. So these are the different components, and there are quite a few parameters that are sort of unknown that you need to adjust to fit the observations. I'll just explain. This is the power spectrum, and what we're just going to, as an ansatz, have an exponent that would have a certain value for scale and variance, but in inflation, the field is rolling down, so you expect the exponent to be a little less than with perfect scale and variance. So that gives you information about the shape, and then there's an amplitude. So in this parameterization, there are just 2 parameters for the primordial power spectrum. One could have more. And then we have things like the current expansion rate, the so-called Hubble constant, the amount of baryons, and it gets put into this ratio, amount of cold dark matter, cosmological constant, and one can sort of add some other stuff. I'll talk about reionization later. And then you try to fit those to the parameter. So this is already very old, but these are the error bars on these parameters expressed in different ways from the WMAP space mission. And you see that you can fix the parameters to if percent or a few percent. And probably the most interesting question is, well, does the model, parametric model fit the data? In other words, is there a model that can explain the data measured at the percent level? So I think I will stop here today. I will talk about polarization at the beginning of the next lecture and sort of explain to you why the CMB is polarized and what you learn from measuring the polarization, which is really quite a lot. So thank you for your attention, and I'll stop now for some questions.
Yeah, thank you very much, Martin, for another exciting lecture and for the preview for the next one. At the moment, I don't see any questions in the Q&A, and Ilya might correct me if I see it wrong. So please, participants, you're welcome to raise your hands, and we can give you the right to speak and ask your question in person. Okay, here comes the first question by Anslin. Anslin, please. Anslin, you're welcome to unmute yourself and ask the question.
Okay, thanks, Francesco. Hi, Martin. Thanks for a good talk.
Hi, nice to hear you. It's been a very long time.
Yes, it has. So my question concerns the B-mode polarizations. I realize you didn't get to it here. In general relativity, you'd have the two polarizations. But in general, you could have a much larger class of polarizations. Do you know how, you know, much work has been done on looking at the effect of these extra polarizations, gravitational wave polarizations on the B modes of the CMB? Or is it very model dependent? Or theory dependent, rather? Well,
actually not. It's not so theory dependent. So I will give you sort of a preview. So these B modes are modes that cannot be represented by a scalar potential. So they're, you know, to use sort of hyped advertising type language, they're the smoking gun of gravity waves from inflation. And this will sort of be one of the focuses of my last lecture, that this is sort of the one new thing, not the only new thing, where one hasn't discovered them yet. I wrote, I mean, when was it? 5 years ago, there was the BICEP team that claimed to have discovered them, and it made this big splash. And I have this article in Physics. Is it called Physics Comment? It's South African Institute of Physics. It's sort of a semi-popular article that talks a little about some of the hubris and where they went wrong. So that might be interesting to look at, but I will, nobody has seen them yet. And there are lots of experiments, both from the ground and space, sort of vying to see those. There are also B modes from the from gravitational lensing, which is something that we haven't discussed. So thank you for inviting this preview.
Thanks, Martin.
Thank you. Are there further questions? Please raise your hand or use the Q&A facility. Martin, it seems your lecture was just too good. and nobody has any queries. Okay, since we continue next week with the mini school series, there is no need to urge participants to ask the question now. They are welcome to make a note and come next week with a full list of questions. Unless, Ilya, do you see questions that I don't see?
Not really. There is nothing in Q&A,
okay,
and
no,
there is nothing in chat.
I'm missing something. Okay, then if that is the case, then Martin, thank you so much for being with us very close today. That's really very nice. And thank you to the participants. Thank you to Ilya, and we will continue next week. You already had a little preview. Yeah. So thank you very much, everyone. Have a good afternoon. Bye. Bye. Bye.